Today, we're going on a journey. We're going to unfold the map of mathematics. And trust me, it's a landscape that's way bigger and honestly, way more surprising than you probably think. So let's dive in. So let me ask you something. When you think of math, what comes to mind? Algebra homework? Calculating a tip? If that's it, you've basically just visited a tiny little village on the coast of a massive, incredible continent. The real world of mathematics is so much bigger and way more diverse than what any of us get to see in school. Okay, so here's the plan. Think of this as the legend for our map. First, we're going to look beyond the classroom stuff. Then we'll explore the two huge continents, pure and applied math. We'll take a tour of the wild, abstract world of pure math, then see how it actually gets used in our world. After that, we'll question the very rules of the game itself, and we'll wrap things up with a little bit of wonder. All right, first up, beyond school math. And, to really get this map, we've got to appreciate just how ancient and deep its roots go. This story, it starts way, way before any classroom was ever built. It really all kicks off with something superhuman, the need to count. We found evidence of check marks on prehistoric bones. And from those super humble beginnings, it just snowballed. Civilizations started building on each other's work. You have the Egyptians coming up with the first equations. Then the ancient Greeks make these huge leaps in geometry. Fast forward to the golden age of Islam, and boom, we get the first real book on algebra. By the time the Renaissance rolls around, math is basically the fuel for the entire scientific revolution. And that sets the stage for the world we live in right now. Okay, so let's jump forward to the modern age. Today, the world of math is pretty much split into two gigantic areas. You can almost think of them like two separate continents, pure mathematics and applied mathematics. So what's the deal with these two? Well, pure math, that's all about exploring for the sake of it. It's driven by pure curiosity, a search for elegance and beauty. It's almost like art, really. Applied math, on the other hand, is all about rolling up its sleeves and building tools to solve actual, real-world problems. But here's the fascinating part. These two continents are way more connected than you might think. And this quote just nails that magical connection. It happens all the time. Some pure mathematician, just following their curiosity, goes off and invents a whole field of math that seems totally useless, like completely abstract. Then, maybe 100 years later, some physicist or an engineer is stuck on a problem and, what do you know, they discover that this old, weird theory is the exact tool they need. It's a pattern you see again and again throughout history. It's incredible. All right, let's start our tour on that first continent, the world of pure math. This is where we get to explore the fundamental building blocks of reality itself. Or maybe just the wild frontiers of our own imagination. And of course, it all starts with numbers. We begin with the simple stuff, right? 1, 2, 3, but you realize pretty quick that's not enough. So we invent fractions. Then we stumble upon these weird, irrational numbers like pi, and then we go even further and invent so-called imaginary numbers. And with each new system, it's like we unlock a totally new layer of reality, with all its own strange and beautiful rules. And that leads to a concept that will honestly bend your brain a little. We all think of infinity as, just infinity, one big idea. But it turns out there are different sizes of infinity. Get this, a mathematician named George Cantor actually proved that there are more numbers between just 0 and 1 than there are whole numbers in the entire universe, even though both lists go on forever. How wild is that? So from numbers, we start building structures. This is where we start sticking variables into equations. That's the heart of algebra, right? But it's also home to fields like combinatorics, which is basically the art of super sophisticated counting. And then there's group theory, the study of symmetry. Think about a Rubik's Cube. Every single twist you make is actually an operation inside a mathematical group. Okay, next stop on the tour, spaces. And trust me, this is way beyond the triangles and circles you learned about in school. We're talking about things like fractal geometry. Those incredible, infinitely repeating patterns. And then there's topology, which studies the properties of shapes that don't change when you stretch or bend them. This is where you get that famous idea that, topologically, a coffee cup is exactly the same as a donut. Why? Because they both have just one hole. And the last major region in pure math is the study of changes. This is the mathematics of things that move, that evolve over time. Calculus is the big one here. It gives us the language to talk about rates of change. And then there are dynamical systems which let us model these super complex, evolving things like weather patterns or even entire ecosystems. And that, of course, leads us to its famous kind of rock star cousin, chaos theory. The idea that something as tiny as a butterfly flapping its wings can end up causing a hurricane on the other side of the world. Okay, so let's recap. We've got all these amazing abstract tools from pure math: numbers, structures, spaces, and changes. Now it's time to cross the bridge over to our second continent, applied mathematics, and see how these strange abstract ideas literally build the world we live in. And I mean it when I say they are everywhere. Physics and engineering, they're basically written in the language of math. Computer science, it was born directly out of abstract logic. Biologists and chemists use math to model molecules. Economics, finance, game theory, even the AI that powers machine learning, every single one of these things is running on a mathematical engine. Check out this brilliant example from a field called numerical analysis. Sometimes a problem is just too hard to solve perfectly. So what do? You approximate it. Imagine you just start throwing thousands of darts, totally at random, at this board. If you count the number of darts that land inside the circle and compare it to the total number of darts you threw, that ratio will get you a surprisingly accurate estimate of pi. It's just a beautiful, simple way of using probability to solve a geometry problem. So we've toured both continents, pure and applied. We've seen the weird and the practical. But now I want us to zoom way out and ask a much, much deeper question. What is all this stuff actually built on? What are the fundamental rules of this whole game? Yeah, this question gets right to the heart of it all. If mathematics is this unbelievably powerful language that can describe the entire universe, what's the language itself made of? What are its fundamental particles, its atoms? Well, the answer is something called axioms. Axioms are just the starting assumptions. They're the basic truths that we don't bother proving, we just accept them. Super simple stuff, like A plus B is the same as B plus A. For centuries, the big dream for mathematicians was to find one perfect, complete set of axioms that you could use to build and prove everything else in math, the whole shebang. But then, in 1931, a logician named Kurt Gödel came along and basically dropped a philosophical bombshell on the entire field, and it's known as his incompleteness theorems. So here's the bombshell. Gödel proved that any set of rules for math, as long as it's powerful enough to do basic arithmetic, is guaranteed to be incomplete. What does that mean? It means there will always be things in math that are true, but that we can never, ever prove are true using our own rules. It's a devastatingly brilliant idea. It means there's no final perfect map. The map of mathematics has no borders. It's a world that we are constantly creating as we go. And you know what? That realization, the idea that math is this vast, unfinishable, totally human creation, it doesn't make it less amazing. If anything, it makes it more so. It brings it all back to the personal, human side of the experience. And this is why people fall in love with mathematics. It's for this feeling right here, that unbelievable aha moment. You know the one, where something that was so confusing just suddenly clicks in your brain and it all makes sense. It's like an epiphany. It's like seeing through the matrix for just a second. You get this glimpse of the deep, beautiful structure underneath everything, which leaves us with one last really profound mystery to chew on. If math is this incomplete game with rules that we humans just kind of made up, then why on earth is it so ridiculously good at describing the universe? Why does this thing we invented map onto the very fabric of reality so perfectly? Now that is a mystery worth pondering.